Okay, today we are going to talk about the polygon angle sum theorems. And there's a few of these to deal with, so we'll jump right in. Okay, so let's first define a polygon. A polygon is a closed figure in one plane bounded by 3 or more line segments. Okay, if we only had 2 line segments, we couldn't close it up, so we need at least 3 line segments. So here's an example of a polygon. Here is an example of something's not a polygon. So the sides can only intersect at endpoints, okay? We can't have sides that intersect with each other. So let's talk about the parts on a polygon. First we have the interior of the polygon, then we have the exterior, and then the side segments connect in what's known as a vertex. The plural of that is vertices, and then the sides themselves, okay? And polygons have a certain number of sides, and that determines what properties they have. So polygons are classified in 2 ways. The first is they're classified by the number of sides. 3 sides are called triangles, 4-sided figures are called quadrilaterals, 5-sided figures are called pentagons, 6-sided figures are called hexagons, 7-sided figures are called heptagons. Hepta, there should be a T in there. Heptagon. 8-sided figures are called octagons. 9-sided figures are called nonagons. 10-sided figures are called decagons. 11-sided figures are called undecagon. And 12-sided figures are called dodecagon. Okay? After 12 sides, we just call it an n-gon, okay, where n represents our number of sides. So a 17-sided figure would be a 17-gon. So the second way to classify a polygon is whether it's concave or convex. Okay? Convex means all your vertices point to the exterior of the polygon and no diagonal has points outside the polygon. And a diagonal is just a line that connects vertices with each other that is not a side of the figure. Okay? Concave polygons have at least one vertex that points to the interior, which means at least one diagonal has lines or points outside that. So if I were to connect these two with what should be a straight line, if I could draw better, the points are outside my original figure, so that makes it concave. Few terms to remember. Remember, equilateral means all sides are equal. An example of that is an equilateral triangle. We can also have equilateral polygons. Okay? Equiangular means all sides are equal, or all angles are equal, sorry. And then a regular polygon is both equilateral and equiangular. Okay? So if we say we have a regular hexagon, that means we are talking a regular 6-sided figure. All the angles in the interior are the same, which means all the exterior angles are the same, which means all the side lengths are the same as well. Okay, so that's a regular polygon. So remember a few terms. Interior versus exterior angles. Interior angles are inside the polygon. Exterior angles extend out from each of the sides. Okay, so each side has its own exterior angle, okay? We also have diagonals, and these are the lines that connect vertices that are not side to side, and or they connect non-consecutive vertices is how we should really say it. So the ones that are consecutive, we don't count, but the ones that are non-consecutive, okay, we do count. And then we can have consecutive sides, which are sides after each other, and consecutive vertices, which are one vertex after another. So when we label polygons, we need to state the shape, which is the type of polygon, and then put labels on the vertices. So for example, we have a hexagon here. So my hexagon should clearly state that it is a hexagon, and then it should have the labels of all 6 sides. Okay? So if I have a square, it would have 4 sides. If I have a rectangle or any other quadrilateral, it will have 4 sides. Okay? And 4 letters that label it on the vertices. Now, what we want to talk about now is finding the number of triangles in a polygon, because when we are dealing with interior angles, this has to do with breaking up our polygon into triangles. And a lot of other concepts deal with breaking up polygons into triangles, such as finding the area inside of a polygon. But here we go with this. So if we connect or break up the polygon with diagonals, okay, which connects non-consecutive vertices, then we break our polygon up into a certain number of triangles, okay? And you can see each of these triangles here, 1, 2, 3, 4, okay? So this is 1, 2, 3, 4, 5, 6-sided figure, gives me 4 triangles. We're going to do an investigation in class that helps you remember what this is. So this brings us to Theorem 3.9, which is the polygon interior angle sum theorem. So what this theorem says is the sum of the measures of the interior angles of any n-gon is the number of sides minus 2 times 180 degrees. And if we think back to our dividing this polygon up into triangles, we divided it into 4 triangles, right? And each of the 4 triangles is comprised of angles from the sides of that polygon, from the interior angle of that polygon. So if we add them all up, we get 4 triangles that each have 180 degrees, okay? And that's how we get the measures of our interior angles for any number of sided polygon, okay? And this applies to both regular and irregular polygons with any number of sides, okay? And we'll derive this formula more thoroughly with an exercise in class. Now, the next thing that we want to talk about is the sum of the measures of the exterior angles of a polygon. And remember, the exterior angles extend out from each side, and those sums are actually constant for any number of sides, and we'll show you a great demonstration that helps you remember this. But all the exterior angles of any number of sides of a polygon, whether regular or irregular, is always 360. So this is a nice constant number that we can use to deal with when we're solving different problems that have to do with polygons. Once again, this is going to be a fascinating lesson in our chapter, and we will do a lot of stuff in class with this. So see you later.